Okay, class. This video is for engineering 2032-15 statistical quality control, and this is for the lecture that we are not able to make on February 2nd. Okay, so we'll continue our discussion still in chapter 3 about normal distribution. This is where we started, and for this entire lecture I'm going to break it down to about 4 to 5 video clips. Each of them will be uploaded separately, and I will create a playlist such that you can view them as a whole. Okay, let's continue our discussion of normal random variable or normal distribution. As we have discussed, since normal random variable is continuous, is characterized by its probability density function, which takes form like this. And in this probability density function, you have two parameters for this distribution. One is mu, which is actually the mean of your random variable x, and the other is sigma, which is actually the standard deviation of my random variable x. And usually people write normal random variable like this. So x follows a normal distribution with mu and variance equal to sigma squared. So for example, if you see someone write a random variable x follows a normal distribution of, let's say, 15 and 25, then you should immediately know that, well, this is a normal random variable with mean of this random variable equal to 15, and the standard deviation, or the variance of this random variable is equal to 25, or the standard deviation of this random variable should be equal to the square root of 25, so that would be fine. Now we discuss the shape of a normal distribution. It's a bell-shaped curve that we're all familiar with, and it's symmetric with respect to the center, which is actually mu. And from the book, and from some simple calculation, we can easily figure out the following fact. If we go one standard deviation to the left and to the right of this normal random variable, then we'll be covering about 68% of all possible values, or all possible cases. If we go beyond another sigma on the left and on the right, then we'll be covering 95% of all possible cases for the normal random variable. If we go another sigma, then we'll be covering over 99%. It's about 99.73% of all scenarios, regardless of the value of your mean and the standard deviation. This is always true. And we discussed this last time. So to calculate the probability related to a normal random variable, there are usually a number of ways we can take. And if we're doing this by hand, the old school fashion, then we usually need to do a standardization. Standardization is a special property of a normal random variable. It said if you have a normal random variable with mean mu and variance sigma square, then the probability that your random variable x is between two bounds a and b, any bounds, can be calculated by standardizing the three terms we have, x, a, and b. It will look like this. Okay. For the upper bound and lower bound, we'll minus mu and divided by the standard deviation sigma, and in the middle we'll have a new random variable z. And z, this random variable is also normal. Sorry, this is also normal, but it's a very special one. Centers at 0 with mean equal to 0 and standard deviation and variance both equal to 1. So, following that, if we write one more step, this will be equal to the probability that a random variable is less than the upper bound minus the probability that z is less than the lower bound. And as we all know, this actually corresponds to the cumulative distribution function of z. So eventually, if we use function phi to represent the cumulative distribution function of a standard normal random variable, then this guy actually will be equal to this function evaluated at this point minus phi a minus mu over c, where phi of z is the cumulative distribution function of standard normal distribution. Okay. I believe you have done and learned this in previous courses. And last the lecture on Tuesday, we did a quick example illustrating how this can be utilized. Now, as I mentioned, if you're doing this by hand, then the good way to do this calculation is to look up a table. The table is sometimes called Z table, which is actually a summarized entries of this cumulative distribution function at different z values. Okay, so in the book you will see this particular example. Okay. You see this phi, and this is what the book is. The z table is organized. And last time we discussed how the z table can be utilized to figure out, well, where to find the corresponding numbers. So coming back here, last time we did an example, okay, and let's quickly review what the example is. That example says the following. The example say, well, I have a certain manufacturing procedure. The procedure will end up with a certain measurement, that's the diameter of a metal shaft, that eventually will follow a normal distribution with mean at 0.2508 and the standard deviation equal to 0.0005 squared. This will be the variance. Okay. And the quantity we're trying to calculate is the probability that out of everything we produced according to this procedure, what is the fraction of parts that will fall between a certain range? And the range is 2485. This is the lower bound, and we have an upper bound 2515. And through our calculation we figure out, well, according to the standardization, we need to do the standardization. So we need to take the standardization of 2515 minus 0.2508 divided by standard deviation 0.0005 and minus phi of 0.2485 minus 0.2508 over 0.0005, and this will give me phi of 3, sorry, 1.40 minus phi of negative 4.6. Now last time in class we discussed, well, for the first term we can figure out, we just have to go back to the table, find 1.40, which is 0.91924. So it'll be 0.91924 minus, now for the second part it's not in the table doesn't have any negative number. So this can be resolved by looking at the symmetric property. The symmetric property of the bell-shaped curve set. Well, I'm looking for phi of negative 0.6. Let's say it's right here. Now this phi, if you look at the table, it's the cumulative distribution function. It also represents the area underneath the curve from all the way to negative infinity to the specific value you're interested in. So for this one I'm interested in 4.6, so the area right here is what you're trying to calculate. So phi of negative 4.6. Since you don't have a negative value in the table, well, we need to use the positive side. And because it's symmetric, if I have 4.6 here, the area underneath the curve to the right of 4.6 should also be equal to the same thing. So it'll be equal to negative 4.6 as well. And this is actually equal to 1 minus phi of 4.6, because if we look at this particular area and this whole green area, the total, so this green area and the purple area should add up to 1. And the purple area is right here, and the green area apparently will be this guy. Now to figure out this purple area we're interested in, we only need to find this value. Now if we go back to the table again, well, again we cannot find it. The reason being this table only runs up to 3.99. Go up to 3.9 right here, and on top you go to 0.09. So this guy corresponds to 0.99. But if you look at the value, this value is very close to 1 already. The reason being, the standard deviation for the standard normal random variable is 1. So 4.6 is already 4 standard deviation away from the center. Okay. According to our discussion earlier, since the majority of the points will be within 3 sigma plus and minus, and you are 4.6, you're already beyond the majority of the points, so that will give this guy close to 1. And of course, when you take the difference, this guy will be close to 0. It makes sense. On the left hand side, right here, the area in this particular area here should be very small. Okay. So that will give it to about 0, and the answer will be 0.91924. And the answer is, well, out of all the parts you produced, about 92% of them can satisfy the specifications. Okay. This is what we did last time. Now we can continue with the same example and talk about something else. Okay. Now let's say a new quality manager comes to the process and asks the following question to the processor, personnel engineer, for instance. Now his goal is to improve this probability. He wants to improve this probability not from 92% maybe to a little bit larger. Okay. But let's say he wants to make sure the products produced can be repaired. Because here we're making a metal shaft and we're calculating the diameter. So he doesn't want the diameter to be too small, because if it's too small, there's no way to repair. If it's large, you can still cut something off. Now what we want is, we would like to have, let's say 95% of products having the diameter larger than a certain bound, and this bound is given as 0.2485 inch. Our question is, can the current process meet this target? We can first do this calculation. Well, this is apparently easy. We're trying to determine if the probability that the diameter is larger than 0.2584 is larger than 95%. We're trying to determine this. Well, we can actually do this calculation, though. This will be equal to what? This will be equal to, if you want to put it back into the x less than a certain value, which sometimes will be easier to calculate, is the opposite of greater than will be minus, and this will be equal to 1 minus probability. And you can do the standardization. Standardization means all you replace this generic normal random variable x with z, and you standardize the constant, meaning 2485 minus 0.2508 divided by 0.0005. So we 1 minus, this is something we did earlier, this is phi of negative 4.6, which is approximately equal to 1, since this phi is equal to 0 approximately. Okay, so this is one example that we can do. Now we can do other calculations. As well. Now let's suppose we have another example. An example is constructed like this. Let's say we are measuring the filling process of a beverage production process, of a beverage production line. Okay. When you fill the bottle with certain liquid, you want to make sure it doesn't go below a certain number, right? Let's assume the filling volume follows a normal distribution. Sometimes it could be a little more, sometimes a bit less. Normal distribution. with mean equal to 16 ounce and standard deviation equal to 0.2 ounce. Now, as a quality manager or quality supervisor, he wants 95% of the products to be good. We want 95% of all products to be acceptable in terms of the filling volume. Meaning have to be greater than a specification limit. Now, while we currently don't know what the specification limit, we can actually calculate. So the question is, out of all products, being produced by this process, what is the filling volume lower limit that cuts off exactly 5% of the products? In other words, 95% of the products will be able to meet this lower limit, and the other 5% has to be refilled or repaired or re-examined. So this is the setup. Now we don't know this limit. This is what we're trying to find out. We can just let this lower limit be, let's say, A. Well, A is an unknown to be determined. And according to the setup, it means, well, the probability or the fraction of all parts being produced, that the volume is less than A. Well, if you feel less, the customer may not be very satisfied, may not be very happy. So you have to deal with this. You don't want this to happen very often. You want this to happen only 5% of the time, for instance, for this particular case, where X the filling volume, and it follows a normal distribution as we have 16 ounce, 0.2 ounce being the standard deviation, so the variance would be 0.2 square. Then probability of the X less than this lower limit A equal to 5%. Here the probability is already given, so you don't worry about the right hand side. What you need to be worried about is the left hand side. So we do the standardization again. So we need my standard normal random variable. So replace X with Z. So first standardize the normal random variable, then standardize the limit. The limit or the bounds will be A minus the mean divided by standard deviation 0.2. We want this to be equal to 0.05. So this is the probability. Now if we look at the table, or before that, we can rewrite this in terms of phi of 1 minus 6, and since this is already Z less than a certain number, we want this to be 0.05. Now if we look at the table, what we need to do is to find 0.05. But if you look at all of them are larger than 0.5 because we're only plotting the numbers on the right hand side. So we need to figure out how to do the conversion again. And the conversion will be done like this. So this is again is our bell-shaped curve. Center is at 0. We want to find this particular point such that this guy will be 5%. We want to find this value. Now, because it's symmetric, we only need to find the other value right here, such that here is 5%, and the rest is 95%. If we can do this, then this part will be done. We'll be able to figure out. We just have to flip the sign to the other side. Now, let's look at the table. Let's find 0.95. And let's say 0.92, 95. Well, it's going to be 1.65 or 1.64. Okay, between 1.64, so 94950. This is 1.64 and 1.65 right here. And 1.65 will be 95053. So I can pick any of the two. If we're doing this by hand, there's no way to be very rigorous. So let's say phi of 1.64 and let it to be approximately 0.95. This is what the table gives me. Meaning if this point is 1.64, then down the right hand side I have this 5%. And for the left hand side I just have to flip the sign because it's symmetric with respect to the center. So meaning if I do phi of negative 1.64, it should be approximately equal to 5% or 0.05 from the discussion. Now we have the same function phi, they have the same result. The only possible way for this to happen is that the intermediate argument are equal to each other. So we just have to take the argument equal to negative 1.64. And continued discussion will be A equal to 16 minus 0.2 times 1.64, or 16 minus 0.328 equal to 15.672. So back to the problem, we can say, well, 95% of all products have filling volume greater than 15.672. And we can also do other calculations. We can do, what if the process are changed, okay, for the same behavior? So let's assume the process are modified. Because the manager said we require 95% of our products to have filling volume greater than the marked volume, which is 16. We want this to happen. Now let's assume the modifications are done such that the new filling volume process will has a new mean but the same variance. So when you operate the machine, you can tune the filling volume a little bit higher, but because of the randomness, you cannot control the randomness. They may still have the variability. So the new filling volume may follow the normal distribution. Let's use y to denote this new filling volume. We'll take another normal distribution with a mean which we don't know yet. Let's use mu to represent. And the variance will be the same as 0.2 squared. But what we do know is, according to the requirement, we want the probability that y is greater than 16 in 95% of the case. Okay. So we want the volume of the products after the modification to be greater than the marked filling volume in 95% of the case. So this calculation can be done in a similar manner. We can first write the larger than into smaller than, so this will be only 5%. And then standardization, so this will be probability that, or you can directly do phi of 16 minus the new mean where we don't know yet, divided by the standard deviation. This should be equal to 0.05 equal to phi of negative 1.64 that we found out earlier. Okay, right here. So coming down, when we have this, the only thing needs to be done is again equate the two arguments. On the left and on the right is negative 1.64. So now mu will be equal to what? Will be equal to 16 plus 0.2 times 1.64, which will be 16.328 ohms. So if you are the quality manager, then you will be talking to the operator of the process to tune up the filling volume average from 16 to 16.328. This way you allow a certain margin of error by adding the average. This eventually will allow this to happen, or it means the new filling volume change will be able to satisfy this requirement. That 95 of the products you produce out of this process will have the filling volume greater than the 16 mark that was specified. Okay. So this concludes this part of the video.